Ever stop and think about how a site like Netflix or Amazon can handle millions of us all at the same time, clicking, searching, streaming, without just, collapsing? Well, the answer is one of the true unsung heroes of the internet, the load balancer.
You know, every big application starts somewhere, and usually it's right here. Just one single server. It's handling everything: the website, the database, all the user requests, the whole shebang. And hey, it's simple, it's clean, and for a little while it works just fine. But what happens when you start getting popular?
Yep, that's the question, isn't it? The dreaded offline screen. If that one server, the one doing all the heavy lifting for your entire app, goes down, maybe for maintenance, maybe it just gets overloaded, what do your users see?
Well, they see nothing, because you just run into what we call a single point of failure. It's exactly what it sounds like. One part of your system that, if it breaks, takes the entire thing down with it. For any service that wants to be reliable, this is a huge, huge problem. It's basically the tech version of putting all your eggs in one basket.
And that brings us to the star of our show today, the load balancer. This is the super elegant solution to our single point of failure problem. Instead of just one server taking all the heat, a load balancer acts like a really smart traffic cop, directing all the incoming requests across a whole team of servers.
So how's it do that? It's actually a pretty clever two-step dance. First, all of the user traffic comes to one single public address. That's the load balancer. Then, the load balancer takes that traffic and forwards it to one of its healthy servers on the back end. And those servers? They're on a private network, totally hidden from the internet. This not only spreads out the work, but it adds a fantastic layer of security too. But here's the thing. Load balancer isn't a one-size-fits-all kind of deal. They actually work at different levels of the network and have different levels of, intelligence. And that brings us to the two main types you're going to run into.
The big difference here really comes down to smarts. A Layer 4 load balancer is all about speed and simplicity. It just looks at basic network info like an IP address and a port, and sends the traffic on its way. Think of it like a mail sorter who only looks at the zip code on the envelope. It's fast and often uses a simple method like round robin, just sending requests to each server one by one. But a Layer 7 load balancer, that one's way smarter. It works at the application level, which means it can actually read the request itself, things like HTTP headers or the specific web page you're trying to visit. This lets it make some really intelligent decisions, like sending all video requests to servers that are specifically beefed up for streaming.
And because of that intelligence, especially at Layer 7, a load balancer can do so much more than just direct traffic. It's got some serious superpowers that are absolutely critical for any big modern application.
Just look at that list. It really goes way beyond simple traffic distribution, right? We're talking about things like ensuring high availability, speeding everything up with SSL termination, and making sure you have a smooth experience with session persistence. These are the things that make the modern web actually work. Let's break down a couple of the most important ones.
Now this, you could argue, is its most important job. The load balancer is constantly running health checks on its servers, kind of like asking, "Hey, you good? You still working?" If a server fails that check or just stops responding, the load balancer instantly stops sending traffic its way and reroutes it to the healthy ones. To you, the user, it looks like nothing ever happened. The service just stays on. That's how websites get that always-on feel.
You know that little padlock in your browser? That means the connection is encrypted. But encrypting and decrypting data actually takes a lot of computing power. So instead of making every single backend server do that work over and over, the load balancer can handle it all in one spot. We call this SSL termination. It decrypts the request when it comes in, sends it safely across the private network, and then encrypts the response on its way back out to you. This lets the backend servers focus on one thing: running the application really, really fast.
Okay, have you ever been shopping online? You add a bunch of stuff to your cart, click to another page, and poof, your cart is suddenly empty? That is so frustrating, and it's often a session problem. Session persistence, or what some people call stickiness, is when the load balancer makes sure that once you start a session on one server, all your future clicks during that visit go back to that exact same server. It's absolutely vital for things like e-commerce, online banking, or anything that needs to remember who you are from one page to the next.
So, we've dug into the what and the how. Let's just pull back for a second and look at the big picture. Why is this piece of technology so incredibly fundamental to the web?
When you put it all together, it becomes pretty clear. Without load balancers, the internet as we know it just wouldn't work. They are the invisible backbone that allows a tiny startup to grow into a global service that millions can use. They provide the reliability, the speed, and the sheer scale that we've all come to expect from basically any major website we visit.
Seriously, think about it for a second. Your online banking, your social media, your streaming services, all your cloud documents, pretty much every complex, reliable service you use every single day depends on this clever traffic cop working silently, perfectly in the background. What's the one thing you couldn't live without?